We're going to talk about the third and fourth types of partial fraction decomposition today. So first, to warm up, let's remind ourselves of what we learned last time, 3x minus 1 over x squared times x minus 2. What we would do with a problem like this is we would write a over x plus b over x squared plus c over x minus 2, because we have a repeated linear term and a non-repeated linear term. So if we have a repeated linear term, we write it once here and then a second time with the squared. And then the non-repeated linear term, we would have c over x minus 2. Now, if I had something of the form 3x minus 5 over x minus 1 cubed times x minus 3, since this one repeats 3 times, I would have a over x minus 1 plus b over x minus 1 squared plus c over x minus 1 cubed. I would have to do it as many times as it repeats. And then I would have d over x minus 3. And then after I solve the partial fraction, I would end up getting a bunch of things and then having to set them equal to 3x minus 5. And we learned that in the previous video. But we're going to learn two more things in this video. We have some non-repeated quadratic factors, and we have repeated quadratic factors. So basically, non-repeated quadratic factors, well, these two, it may not be as obvious, so we're going to factor the denominator. And so when we factor the denominator here, we get x squared plus 1 and x squared plus 4. And then down here, if I factor the denominator, what I end up with factoring by grouping, I would have x minus 4 times x squared plus 9. And so learning that factoring was an algebra 2 type of thing. But what we would have in this case is, notice that we have these quadratic factors that you can't factor any further. So if you look at x squared plus 1, x squared plus 4, x squared plus 7, x squared plus 9, x squared plus 3 over here, and then x squared plus 3x plus 1. Notice it doesn't just have to be a binomial. You can also have a trinomial. But if you had x squared plus 3x plus 1, that doesn't factor any further, so you can't break that down. So in any of these cases, if you have these quadratics that don't factor anymore, you have to do something similar to what we did with these linear terms, but it's just a slight difference. And the slight difference is anytime you have a quadratic term in the denominator, instead of just writing something in the numerator that is constant, you have to write a linear term and a constant term in the numerator. So we would have ax plus b over x squared plus 1 plus cx plus d over x squared plus 4. That would basically be what we would write. And it looks like I have to drag them all separately. But that would be what my partial fraction decomposition looks like. Now, if I'm writing this one, notice I have this x squared. That's a repeated linear term. So I already know how to do repeated linear terms. I would have a over x plus b over x squared. And notice that this is treated as a linear term that's squared rather than a quadratic term that's not squared. And so we have to kind of understand the difference between something that looks like x minus 3 squared and something that looks like x squared plus 3, where this is repeated linear and this one is non-repeated quadratic, because I can't factor this x squared plus 3 anymore, but this x minus 3 squared or x plus 3 squared or anything like that, that is factored into linear terms as much as it possibly could be. So then finishing this problem, I now have this quadratic term. So I'm going to put cx plus d. Notice anytime you have a quadratic term, you put cx plus d, or some linear and a constant in the numerator. And then I have x squared plus 7 in the denominator. And then that finishes that problem. Now this one down here, I have one linear term. So I have a over x minus 4. And then I have one quadratic term. So I would have bx plus c over x squared plus 9. Now, if I have a repeated quadratic factor, that's going to end up looking identical to what we did when we had repeated linears. So if I repeat something, I just have to repeat it more than once. So here I have one linear term. So I have a over x. Then I have this quadratic term, but it has to show up twice. So I have bx plus c over x squared plus 3x plus 1. And then I have to write it one more time, dx plus e over x squared plus 3x plus 1, the whole quantity squared. And I know I ran out of room, but fortunately I can make room. Then this one down here, I have a quadratic term and then another quadratic term that's repeated. So I have ax plus b over x squared plus 1. That one only shows up once. Cx plus d over x squared plus 3. That one shows up twice, so I have it showing up once there. And then I have ex plus f over x squared plus 3, the quantity squared. So irreducible or non-reducible quadratic factors. They can be combined with either type of linear factors, as we showed on the previous slide. First thing you do is factor the denominator if you have to. Then each linear factor gets treated as we did in the previous video, and x by itself is a linear factor. Each quadratic that cannot be reduced and has a power of 1 gets treated as ax plus b in the numerator, and then whatever the quadratic is in the denominator. So here's an example. X plus 1 and x squared plus 4 are the factors of the denominator, and we can't reduce either one more than that. So we put a over x plus 1, and then bx plus c over x squared plus 4. Then we get a common denominator, like we have done since Algebra 2. So we multiply the x squared plus 4 over to the a, and we multiply the x plus 1 over to the bx plus c. We do a lot of distributing and simplifying. And so what you can see is if I group all of the x squared terms, I have a plus b. If I group all of the x terms, I have b plus c. And if I have all of the constant terms, I have 4a plus c as my constant terms. So if I'm looking at what these have to equal, this has to equal 0 because there's no x squared term up here. This has to equal 0, and this has to equal 1. So, when we go down here, this is exactly what our answer said it was. And so now what we can do is we can look at each of these individually and figure out what we would do. So if a plus b equals 0, that means b equals negative a. And if b plus c equals 0, that means b equals negative c. So I can just simplify those things. And so then what I can do is I can do some problem manipulation if I needed to in order to solve something. And so I can solve for A or B or C or whatever I wanted to solve for first. But what I'm going to do is I'm actually going to solve for B first. So what I will do, I'll also notice that A is equal to negative B and C is equal to negative B. So what I can do down here is take this and say if A is negative B, I have negative 4B. And if C is negative B, I have minus another B. And that equals 1. So negative 5b equals 1, or b equals negative 1/5. And then that means that I can figure out what a and c also are. A must be 1/5, and c must also be 1/5. So what that means, if I write my answer, if a is 1/5, I have 1/5 over x plus 1, plus b was negative 1/5, and c was 1/5. Then I have x squared plus 4. So this would be my answer. I could write this a whole lot nicer if I realized that all of my constants are 5. So I can say 1 over 5 times x plus 1, or all my denominators are 5. 1 over 5 times x plus 1. And then I can also factor out this negative in the front. And so then I could have x minus 1 over 5 times x squared plus 4. And then that would be the answer to that problem written as nice as I can make it. So then I can also do the same thing in this problem. Notice that x cubed plus 27 factors with SOAP. So that's the difference of two cubes. And x squared plus 3x plus 9 is not factorable. So that means that I can just stop there and say bx plus c and kind of figure out what goes on from there. So I multiply the a by the x squared plus 3x plus 9. I multiply the bx plus c by the x minus 3. And then I continue to go on from there. And so then what I want to do is I kind of want to group the things. So a plus b is x squared stuff, and that equals 0. Then I have 3ax and cx and minus 3bx. So I have 3a minus 3b plus c, and that has to equal 26 because those are all coefficients for x. Then I have 9a minus 3c, so 9a minus 3c must equal 30. And so now, what I would probably want to do is I would probably want to make b equal to negative a. So then I can rewrite this red one as 3a plus c, which is 6a plus c is 26. And then I have 9a minus 3c equals 30. And now I can solve this system. So I'd probably multiply this red one by 3. So I have 18a plus 3c equals, that would be 78. Then I have 9a minus 3c equals 30. So when I add these together, I get 27a equals 108. So I know that a equals 4, which means b equals negative 4. And c, well, I have to do a little bit more work in order to get c, but that would be 24 and then subtract it over, so c equals 2. So if I want to write my final answer for this problem, I would end up with 26x plus 30 over x cubed minus 27 is equal to 4 over x minus 3 plus negative 4x plus 2, which means I could also factor out this negative if I wanted to and make it minus 4x minus 2. Remember, if I factor out the negative, then the sign has to change, over x squared plus 3x plus 9. Then I also have one more problem that I did for you already that I'm not going to do, or this video would be 45 minutes long. But I wanted to show you that if I had a repeated factor, a repeated linear one, I could do this problem with 3 things in it, and then I would have this. And then I did some distributing here and here. I grouped all these things together. This would equal 0. all the x cubed things equal 0, all the x squared things equal 0, all the linear terms equal 22, all the constant terms equal 8 in this problem. So then you do a lot of system simplifying and system subbing and stuff, and you get b equals 5, a equals 2, c equals -2, and d equals -7. So I'm just showing you that this is something that you can do. It just takes a lot more work. Okay, now irreducible repeated quadratic factors. You factor the denominator. Each linear factor gets treated as you did yesterday. Each quadratic factor that we did in the first part gets treated like we did yesterday. And then each quadratic factor that has a power greater than 1 gets treated like yesterday's repeated factors, just like we showed a couple slides ago. So anything that gets repeated, like with a squared or a cubed or whatever, we just keep going and we continue to repeat. So in this problem, notice that x squared plus 16 squared, that can be repeated as x squared plus 16 and x squared plus 16 squared. And so what I would do is I would then distribute things. Notice that this one is missing an x squared plus 16. And then this one is missing nothing from its denominator. So what I would do then is I can then distribute things. I have ax cubed plus 16ax plus bx squared plus 16b plus cx plus d. And then what I do is I start looking for all these things that I need to have. So if you look at this, a must equal 0 because it's the only x cubed. Actually, a must equal 1. Reading is a skill. So notice that I have 1x cubed up here, so a must equal 1. There's only one x squared term, so b must equal 0 since there are no x squareds up here. Then I have 16ax and cx, so I have 16a plus c. That has to equal 0. So if I know that a equals 1, that means c equals -16. And if I look at the constant terms, I have 16b plus d. So if I'm looking at the b term has to equal 0. So 16b plus d equals 1. Since I have this plus 1 up here. The b has to equal 0, so d equals 1. So I have these 4 values of variables. And then I could write my final answer. So x cubed, was it plus 1? Over x squared plus 16 squared is equal to x over x squared plus 16 plus -16x plus 1 over x squared plus 16 squared. And then, like I have in the other problems, if I wanted to, I could factor out this negative sign and make it look like this. Here's one more example for you. So if we had 2x cubed plus 11x minus 3 over x squared plus 3 squared, that's a repeated quadratic term. So what I would do is I would, if I were doing partial fraction decomposition, rewrite it as ax plus b over x squared plus 3 plus cx plus d over x squared plus 3 squared. Then very much like the previous problem, I would realize that ax plus b has an x squared plus 3 missing from its denominator. Cx plus d has nothing missing from its denominator. And then I distribute this stuff. And then I would notice that the only x cubed term is a, so that has to equal 2. Then the only x squared term is b, so that has to equal 0. And then I have 3a and c both have x coefficient, or are the coefficients of x. That has to add up to 11. And 3b plus d has to add up to -3. And so then You just substitute 2 in for A and 0 in for B, since we already know those, and get C equals 5 and D equals -3. And so that is our final answer. 2x over x squared plus 3 plus 5x minus 3 over x squared plus 3, the quantity squared.